Okay, so everyone can see my screen, right?
Yeah, yeah.
Okay. So hi everyone. Today I'll be talking about electrical conductivity in random alloys using KKR-CPA. So briefly, this is sort of the outline of my talk. So I'll sort of discuss CPA very broadly within the within KKR method, and then we're going to talk about how conductivity is implemented. This is basically to the Kubo-Greenwood equation. So how we can convert that into Green's functions, which is what we use in the KKR method, and then how we can sort of adapt that to the random alloy to get a CPA expression for conductivity. Then we have implemented that in Must. So I'm going to show the results for some binary random alloys. And then I'm going to give sort of a brief overview of the cluster average CPA, which is a technique to include short range order in CPA. And then how we can sort of ideas on how we can implement conductivity within cluster average CPA so that we can get conductivity of alloys which have short range order. And then some of the limitations that we're facing right now. So CPA, the basic idea is you have a random system. There's a high chemical disorder because you have different species and different arrangements. And instead of trying to deal with all the different arrangements or trying to make, say, supercells, you can replace your random alloy with an effective medium, which is essentially a single element pure crystal. And you find the effective medium such that it behaves like your ensemble average. And there's a great computational advantage in doing that because if you've done supercell calculations, those are very expensive, and CPA calculations are quite have very less computational cost because oftentimes you are just doing a single atom calculation. And sort of a fundamental approximation in within the CPA is the single site approximation. So basically, this is an approximation of complete randomness. So let's say you have a binary with red and blue, and they're, say, equiatomic. That means each site has 50% probability of being red and a 50% probability of being blue. And a particular site belonging to a species, red or blue, doesn't influence the distribution of chemical species of its neighbors. So those are chemical species are not correlated. And within this approximation, the way you calculate the effective medium is you make single site impurities. So you make single site impurity by putting in a red atom. You calculate the tau matrix associated with this configuration. Then you get put in a blue atom, calculate the tau matrix, and then you take a concentration weight average. And that this equation one is essentially the mathematical expression of the single site approximation. And one and two, in fact, you combine to get a self-consistent algorithm. So you can get self-consistently find this medium, uh, and that's how you implement CPA within the KKR approximation. And there are some more terms that I want to define, which are going to be a bit useful when we discuss the conductivity formulas. So this D matrix is given by this expression here, where this tau CPA is your multiple scattering path matrix within CPA. T alpha is the T matrix of alpha species. TCPA is T matrix of a CPA atom. And you can also define an X matrix, which is connected to D to this formula. And the reason for doing that is the average of the X matrix is 0 within CPA. So this is a sort of alternate expression of the CPA condition. So you can either show the CPA condition as the concentration, the average of tau matrix is tau CPA, or you can show that the average of X matrix is 0. In fact, in the must code, I think this is how this is used for calculating the iterations, the CPA medium, because this converges better. So now let's move on to conductivity. So if you want to calculate conductivity from first principles, there are a few different ways of doing this. So you can use a semi-classical Boltzmann transport equation, which requires you to do band structure calculations. You can use the Randauer formula, which is essentially equivalent to like imposing some sort of potential and trying to calculate conductance. But the formula that we are going to use is the Kubo-Greenwood formula, which is a linear response. So basically, if you have a Hamiltonian, which you consider as your base system Hamiltonian, and you put in an electric field which you can which you take as a perturbation, then you can use the linear response regime, which is given by this expression here, which is Ohm's law. Then conductivity at 0 Kelvin can be expressed through this formula here. And these angular brackets represent expectation values with respect to the unperturbed Hamiltonian. And we can convert this through some algebra to this equation 2 here, which is referred to as the Kubo-Greenwood formula for the DC case. And here alpha and alpha prime are eigenstates of your unperturbed Hamiltonian. Now this is sort of the starting point for the system. So now we want to convert these wave function terms into Green's function, because that's what we have in the KKR method. So if we start with this, then we can use this formula here. This outer product times the delta function can be expressed in terms of the imaginary part of the Green's function. And you have essentially those type of terms here. So if you use this formula, you can get this expression for conductivity, which is basically some product of the current matrices, the current operator and the imaginary part of the Green's function. Now this can significantly be simplified. First of all, we can get rid of the imaginary parts, and sort of the simple way of doing that is to write it as a difference between the real energy and a slightly imaginary energy Green's function, where delta is a small imaginary part. And if you do that, you can see that there were two Green's functions here, and each of them, now you're inserting two more. So you'll have four terms. And you refer to each term as sigma tilde, where sigma tilde is now given as this trace of this ensemble average of current operators in Green's functions. Now, whenever we refer to conductivity in the formula terms, we will refer to sigma tilde. So it is then given that if you implement this, you need to calculate sigma tilde at 4 different energy points and then take this a limit. But for all the formulas that come after this, those formulas will be for sigma tilde. And sigma tilde will be referred to like commonly as conductivity. Now we want to express this trace as something we can deal with. And to express trace, you need a basis. So sort of simple basis to use is the position basis. So within the position basis, you can express is at this integral here, where you have one trace, so you'll have one integral, and then you introduce another complete set of states in between, so you have two integrals. And now we know what the Green's function is within the KKR. So you know the Green's functions can be expressed in terms of the single site solutions. There's a single site regular solution Z and the tau matrix. There are some additional terms here as well, which involve the irregular solution, but those terms are real, and we are only focused, if you remember, the imaginary part of the Green's function, so we can ignore those terms. And if you put this expression here, this double integral factorizes into two separate integrals. So, and you use the non-relativistic expression for the current matrix, which is what we will start with, which is the non-relativistic expression. You'll get this sigma tilde here, where J is the current matrix given by this last integral here, and tau is your multiple scattering path operator of your system. And these angular brackets are your ensemble average. These L1, L2, L3, L4 are angular momentum indices, and M and N are site indices for a system with multiple atoms. Now, at this point, this is a sort of in some sense, implementable equation of conductivity. So we can actually at this point implement this for a large system and get the conductivity.
May I
But
have
then,
one question, just small? Uh, you don't have any orbital indices here, multi-orbital kind of.
yeah, I mean, angular momentum indices are
Oh, okay.
orbital.
Yeah, yeah. Okay.
Yeah, yeah. So these L's are, each capital L is like small l comma m. So
Yeah.
they go, yeah, so they go over, we use L max up to 3,
Yeah.
which is the f orbital. So
Yeah.
use it, yeah. So we can implement this for a supercell, but then that will be quite expensive because you need to take a very large cell in order to ensure that you have sufficient randomness, and that can be not a very practical way. But then the best way to then deal with it is to do CPA. But then that requires significantly more algebra and modification, because we need to sort of convert this expression into something that has CPA variables. So you want this in terms of tau CPA. And so let's look at how we can do that. So firstly, let's deal with these indices over the site. Now let's open the M index. So let's say you have m equal to 0 term, m equal to 1 term, and so on. So you can break this into n terms. Now in a CPA medium, it's just a single element. It's like a pure crystal, and you have translational symmetry. So there should be no difference between one site and another site, which means all of these terms should be the same. And there's a factor of n here, and you'll get a factor of n. So those will cancel out. So that means you have just the tilde in terms of one term n, and you've set m equal to 0. So that is the first simplification you make. Now, at this point, the algebra becomes quite complicated. So there is a paper by Butler, which introduced all of this, and I'll put a link to the paper in the end, which has all this algebra in good detail. But the sort of base methodology that is used is this tau of the system. You can write it as tau CPA plus some sort of excess scattering correction term. So, and this expression is not just valid for CPA, you can have any effective medium. So you can consider tau of a system as some correction over any effective medium tau. And you can express this T, which is again, it's like some excess scattering term in terms of the X matrix, which I had introduced before, as this sort of series over here. Now, within the single site CPA, you can ignore some correlations. So you can take an average over here and take this product of averages. And now, as I mentioned before, the average of the X matrix for CPA is 0. But if you make a single site impurity at M and you force that site to be species alpha, then this will be X alpha. So that's basically the method that's used repeatedly. So you insert the expression for tau in the conductivity in terms of this, and then you take these ensemble averages. So you keep repeatedly doing that, and you can get a final expression. And this is what the final expression looks like. So you can write sigma tilde as sigma tilde 0 plus sigma tilde 1. Now sigma tilde 0 is a sort of single site term which is quite small as compared to sigma tilde 1. It's at least 2 orders of magnitude smaller. So we're not really going to go into that. The important term here is sigma tilde 1, and that is given by this expression here, where this 1 minus chi omega inverse is referred to as the vertex correction term, which is, I'll get into that in the next slide. And chi is given by this expression here, which is the product, the Brillouin integration of the product of two tau matrices. And this omega is the average of two X matrices. And the J tilde is the product of D tilde and D with the current matrix. So basically this expression is what is implemented in must to get the conductivity. Now let's look a bit closely at this vertex correction term. So if you look at this omega matrix, as I mentioned, it's the average of the two X matrices. So you can, in some cases, make this approximation where you assume that the average of the product is the product of the averages, and the average of an X matrix in single set CPA is 0. So then you can make this omega matrix as 0. And if that's the case, then this 1 minus chi omega inverse just becomes 1. So this means we're neglecting vertex corrections. And this is something that can be desirable in some calculations, because this 1 minus chi omega inverse can take some computational time, because you're calculating the inverse of large matrices. And if you ignore omega, then it can save some time while you're doing a calculation. But then for some systems, you miss out on, you don't get an accurate conductivity value. And for some systems, you do. And some physical intuition you can get for this term by looking at the Boltzmann equation. So the Boltzmann equation for if you apply an electric field is this expression here, where this Q prime is probability of an electron moving from state Q to Q prime. And these G terms represent the deviation from your equilibrium distribution, which is the Fermi-Dirac. So if you ignore the scattering in term, which is the second term here on the right, so you have a scattering out term, which is from Q to Q prime, and a scattering in term, which is from Q prime to Q. So if you ignore that scattering in term, then the solution you get compares, like matches with the non-vertex correction solution. So in some sense, ignoring vertex corrections essentially means you are ignoring the scattering in terms. So we'll look at some examples of systems where vertex correction makes a big difference and where vertex correction doesn't. Uh, Also, another important aspect when we're implementing this equation is, if you had noticed before, so if I go to one slide before, this chi and omega are fourth order, so they have four indices. And this product here is a sort of like a tensor product type, so you have fourth order. And we would like to sort of make this into a matrix product, which is more easy to deal with. So to do that, you sort of compress the indices. So you put two indices together to make one, and then you can convert this into some sort of a matrix product. Your chi and omega then become just regular matrices. And the relation between these compressed indices and your regular angular momentum indices are given here. Just the slight downside of this is now each index is the square of what it was initially. So if L max is 3, then initially the angular momentum indices were going to 16, but now they'll go up to 16 squared. So this chi matrix and this omega matrix is a 256 cross 256 matrix, uh, which is slightly large, but is larger than your regular angular momentum matrices. So this has been implemented in Must with the vertex corrections. So let's look at some examples. So the plot on the left was obtained using the SPR KKR code by Hubert Ebert. And there are multiple different plots here. What we need to compare is this black dash plot and this plot with the red crosses. So the black dash plot is single site CPA without vertex corrections, which you can see compares quite well with ours. It's about 15 microohm centimeter, which is also what we have here. And the red crosses are including vertex corrections. So that's about 5, slightly over 5 microohm centimeter, which is also what we have here. So you can see that for copper zinc, it's important to include vertex corrections because it does make quite a difference. And this calculation was done at quite high K points. So it was done at 96 cross 96 cross 96 K points. And we use the LDA as the exchange correlation potential. Now, the second system we can look at is silver palladium. Again, the left plot, there are three plots here. The blue one is the experiment. Uh, and these two, the pink and the green plots, are neglecting and including vertex corrections, respectively. And this was again done using the SPR KKR code. And the one on the right is using must. So again, you can see that this compares quite well with their computational result. It does not compare well with experiment, which we're not quite sure why that is. So one practical reason is maybe there were some defects in the sample, some dislocations, which may be adding to the resistivity, which we are not modeling in our calculations. So that's one possibility. Uh, but you can also see that in this case, vertex corrections don't really play that big a role. So the decrease due to vertex corrections is slightly significant at high silver concentration, but at the peak, it's not much of a difference. So that's the behavior of this system. Also, in the copper zinc, you can see that it follows the Nordheim rule, which shows that the resistivity goes as concentration times 1 minus concentration, which is a parabolic shape. But in the silver palladium, the Nordheim rule is uh, not valid. And in general, we don't expect the Nordheim rule to be true everywhere. It's just for some systems it does match. Then we can look at a few more systems. So gold palladium, uh, what we need to compare with is this non-relativistic expression here on the left, and you can see that it matches quite well. Even without the plot by must doesn't have vertex corrections, but it still compares quite well. You can see this characteristic drop from 50 to 60 has been captured in both the plots. And finally, we can look at copper palladium. So again, we need to compare with the non-relativistic plot here, which is the open triangles. And again, there is a sort of good comparison between uh, previously computed results and our result. So these results sort of show or act as a validation for our code, which demonstrates that the conduct we are getting physical proper values of conductivity. Now, obviously, we're using single site CPA, we're using complete randomness. You're missing out on correlations, you're missing out on short range order. And most alloys that we see in real life are short range order. And short range order does significantly affect resistivity. So, and other lot of other physical properties as well. So we would like to capture the short range order effect within CPA. And there are multiple ways to do that. So there is your ECM CPA embedded cluster method. There's a non-local CPA, and there are other methods. But our method is the cluster average CPA. So the idea is similar to single site CPA, but where in single site CPA you would put a single atom, a single impurity of red atom or a blue atom. In this case, we're putting that, but we're also putting average neighbor atoms. So you're putting these green neighbor atoms and yellow neighbor atoms. Now, these green and yellow atoms are essentially, again, sort of weighted averages of the red and blue, but these weights control the type of ordering that you want. So, for example, let's say you want to model a system where short range order is present, so where unlike neighbors are preferred, then your W12 parameter and your W21 parameter, they will be one, they will be prominent, and your diagonal parameters will be zero. So that's how you would capture that sort of ordering. And if you want to capture the exact opposite, you want to capture clustering, then your diagonal parameters are your main parameters, they would be one. Your off diagonal parameters would be zero. So those are two extreme examples. You can sort of tune these parameters to get the type of ordering that you want. So that is the cluster average method. And there's a huge advantage to using this approximation, this approach, rather than putting in real atoms, which is what ECM CPA does or non-local CPA does. You actually put in real clusters and you assign weights to those clusters. And the problem is that as you scale the number of species in your system, uh, the number of clusters that you're going to have to put in to capture the short range order also increases. But if you use these sort of effective parameters, then the computational cost does not scale significantly with the number of species present. It only scales with the size of the cluster that you put in. So if you put in a cluster that includes central and near neighbor atoms, that's like the simplest. If you put in, you can also put in a cluster that has next near neighbor atoms. That will take a bit more time because you're dealing with larger clusters. So the computational cost, it scales very well with number of species. So you can do this calculation for high entropy alloys as well, which have like 5 or 6 different elements, and not have to worry about the different possible clusters that you have to put in. So that's how this method works. So let's look at a simple example of copper zinc, a BCC. So the type of short range order matrix that we put in is given here, where we parameterized it using the copper near neighbor parameters. We varied that from 0 to 1, and you can see that the lowest energy is associated with the copper parameter being 0, which is associated with like unlike neighbors being preferred, which is indeed what we know about copper zinc, because we know that copper zinc is a B2 type system where copper and zinc alternate. So this shows that you can use CACPA to sort of get the behavior, to get the short range order behavior of systems. And also there are 2 ways of doing CACPA. You can just use the single site CPA medium and put in your average cluster and get the result. That's a sort of quicker way of doing things. But then you can also develop a self-consistent iteration to get a CACPA T matrix and a CACPA iteration scheme. And in this case, it does not make a significant difference because the simple cluster and CPA medium seems to be capturing most of the short range order. So this is an example of how we can use CACPA to get, say, the energy. You can also get the density of states. You can get CPA, single site CPA density of states and CACPA density of states. And then you can very clearly see sort of the difference between the two, and you can identify the short range order, because the CACPA density of states will look much less broad, much more peaked, because there's less randomness in the system now. Now, we would like to implement conductivity within the CACPA, and the way to do that is very similar to CPA. It's sort of the same methodology, but now there are a few more indices you have to worry about. So again, you can write your sigma tilde as sigma tilde 0 and sigma tilde 1. I'm ignoring sigma tilde 0 for the moment because I expect this to be smaller, uh, at least an order of magnitude smaller than sigma tilde 1, which is the dominant term. So you have a very similar looking expression, but apart from angular momentum indices, you also have these L, M, Z, and R indices, which go over the cluster, the different atoms in your cluster. So now the chi matrix is an 8th order because it has 8 different indices, and you have the same tau matrix, but you also have an exponential term over here, where these R, L, RZ, RR, and RM are position vectors to your neighbor atoms. And your tau LZ, your tau matrix is now a block matrix, where each individual block represents the tau matrix, the scattering between 2 different sites in your cluster. So you have tau LZ and tau RM here. And similarly, you have an omega matrix, which has cluster indices, and the J tilde matrix. So one thing, there are some things that give us confidence about this expression. The first one is that it's very similar to CPA expression. And in that, if you set M, L, Z, and R all to be 1, if you set the cluster size to be 1, this expression will just collapse to the CPA expression. So that's sort of one basic theoretical test you can do. Also, one sort of potential problem here is that We want to convert, again, as we did for the single site CPA case, instead of dealing with all these indices, convert this into a matrix form by compressing these indices together. So you can do that here. You can get compressed indices and get this into a matrix form. But now each sort of compressed index has two cluster indices and two angular momentum indices, and they are related by this expression here. So the CK1 can be expressed in terms of the two cluster indices and two angular momentum indices. But now each index goes over the cluster squared times L max plus 1 to the power of 4. So let's say you have a BCC system and you want to include correlations up to first near neighbors. So that means that there are 8 near neighbors in BCC plus one central atom. So that's a nine atom cluster. So each index goes over 9 squared times 4 to the power of 4. So that's 81 times 256, and that's like 20,000. So these chi and omega matrices are 20,000 cross 20,000 matrices. If you want to include short range order, that's extremely large. And we'll discuss some of the pitfalls of that slightly later. Also, we can compare this expression to non-local CPA. So there is a conductivity expression derived for non-local CPA, and that's also a cluster-based technique. So they have a very similar expression to ours. You can see that you have the same tau matrices and the exponential products, and their dimensions is, you can see, cluster squared, angular momentum squared. So that also gives us some confidence in our expression, because both the non-local CPA and the CA-CPA techniques are both cluster based. In you're putting clusters into your medium. It's just the type of clusters differ. And one, again, basic sanity check that we can do is you can set your cluster size to be 1, do a calculation, and see if that calculation gives you values that are similar to single site CPA. And second, you can do a full cluster calculation of 9 atoms, but you set all your neighbor atoms to be CPA, and that should also give you the same result as single site CPA. And you can see that that is indeed the case based on this graph. These values themselves are not physical, because to save time, I've done them at very low K points. So this is 8 cross 8 cross 8, which is extremely low. So the values themselves are not physical, but what we want to see is that they're similar to each other. And that's another base check. Now, we would ideally like to test this for actual systems by putting in short range order parameters and seeing whether how they compare. But there are some computational limitations that we're facing, which is, for one example, a single CPA calculation at 8 cross 8 cross 8 takes 30 seconds. But if you do an SRO calculation, which is the CA-CPA calculation, and you include, say, 9 atom cluster and L max equal to 3 on a single core, that takes about 14 hours. And this is at very low K points. And we want to scale this for production runs at least 1 million or more K points. So that can take a lot of time. Also, since we're dealing with like 20,000 cross 20,000 matrices, and each element is a complex number, so it's like 16 bits and 16 bytes. So you have a high memory usage. So for BCC, for 9 atom cluster, you have about 80 GB of memory. And FCC, there are 13 atom, because you have 12 near neighbor atoms in FCC. So that's like about 360 GB of memory. So there's extremely high memory usage, and there's extremely time consuming. So that's a sort of limitation. And we're looking to see how we can sort of get past this. And there are a few approaches. So the first approach is to, of course, reduce the cluster size, because ideally you would like to take all the near neighbor atoms and use all of them to get SRO, but we don't really have to do that. You can just take, say, 1 or 2 atoms from the near neighbor shell and use those to get correlations. So which is what we're doing right now. Also, we need to identify systems where that many K points are not needed to get convergence. So for copper zinc, very large number of K points are needed, but there may be systems where that's not true. Also, we have many independent loops in the calculation, many different indices. So we would like to we would like to parallelize those indices and uh, maybe do some memory parallelization to get sort of distribute these large matrices. So those are some possible approach. So the best is of course the first one. So currently right now we're putting pair clusters. So basically we're just putting the central atom and one atom in the near neighbor shell and seeing whether that captures some of the short range order. So we are in the process of doing that. So to summarize, you can express the Kubo-Greenwood equation in terms of Green's functions and tau matrices, which is what we use in KKR. With some significant algebraic modification, you can then adapt this to single site CPA, and then we've implemented that in Must, and that can be used to calculate with vertex corrections the conductivity for random alloys. Now, we want to deal with short range order within CPA, so we use CA-CPA, and in a similar fashion, you can get a conductivity expression for CA-CPA, and we're testing that right now and trying to get past some of the computational limitations of doing that. Also, right now, all our expressions are non-relativistic, and we're not really dealing with spin. So in the future, we do plan to implement relativistic versions of this conductivity expression. It's actually very similar. It's the same expression, but where we had used the current operator d by dr, we had used the Schrodinger equation operator, but then we would use the Dirac equation operators here. We would use J is E times C times the alpha. So we would use that, the relativistic current expressions, and our indices would not go over from 0, 1. They'd go 0, half, 1, 1.5. So you'd have spin as part of those indices. So if in the future, we plan to implement that expression. And if we do that, of course, we can then study spin transport, and then we can study sort of exotic properties like the anomalous Hall effect, where because of spin orbit coupling, you have the quantization. So that is sort of a future plan. And also, as I mentioned, a lot of the single site CPA math and this sort of methodology for it comes from this paper by Butler, which if you're interested in seeing like exactly how you go from the Kubo-Greenwood expression to CPA with all the steps, most of the steps in between, it's given in that paper. Also, there's a nice comparison between this expression and the semi-classical Boltzmann equation expression, which shows sort of similarity. So yeah, so does anyone have any questions?
I would have two questions actually. So the first one is, so I saw, so you're always using KKR-ASA for all of the plots that you showed. Is there any specific reason for that, or was it just for reducing the computational effort?
Yeah, we are using KKR method. So our code, the must code has KKR, uses KKR to get the Green's function.
I meant if you're using, why are you using ASA and not just normal muffin tin?
Oh, ASA. That was I wanted to compare with their result. So this result was calculating using ASA.
Okay.
The Hubert-Ebert code uses ASA. So that's why, in order to get a fair comparison, we also used ASA.
And did you notice some differences like between ASA and muffin tin?
Yeah, that's a great question. We noticed a lot of differences. So especially for the case of copper, zinc, and silver, palladium, we noticed that using muffin tin, the resistivity was higher. So the resistivity actually compared quite well with experiment. So it was at its peak about 40 micrometer centimeter using muffin tin, but using ASA, it was smaller. So, but then there's no sort of guarantee that that will happen in all the systems. But we did notice some significant differences between ASA and muffin tin.
So this.
Yeah, I think the picture on the right hand side is for muffin tin calculation, right?
No, it's
ASA.
We use
ASA. Okay. I think you have one of the is a silver. Okay. I think the other figure 4.
Yeah, these two. So this is muffin tin.
Yeah.
This both left and right hand side are muffin tin.
Yeah, the right hand side is muffin tin, but the left hand side is ASA. I see. Yeah, muffin tin give a larger conductivity, resistance. I'm sorry, use resistivity.
Yeah, at least for some of the systems that we have observed, we have noticed that muffin tin gives slightly larger, but
larger resistivity now.
Yeah, but we spoke with Hubert Ebert because we wanted to get some comparisons, and they had mentioned that they had done some tests, and sort of in general they didn't find anything. They didn't find this to be a significant trend. That they said for some systems they found ASA higher, some systems they found muffin tin higher.
And the other question is about the K points. So did you really investigate where these differences are coming from? Because I mean, okay, it's a linear response theory. Okay, maybe there are some dependencies there, but this really is like shockingly high. That's why.
Yeah, so I think one important point to notice is that the method of generating K points is special K points. So maybe if we use say tetrahedron method, or we use more adaptive methods of K point integration, then we might not need that many K points. It's if we identify, for example, in this, so in this integral, if we identify the places in the Brillouin zone where this function is peaked, then we can just use high density at those areas and sort of make an adaptive K point grid, and then that would require much K points, but we're not really doing that. So as a result, I think that's an important reason for why we need so many K points.
At the moment, tetrahedron method has not implemented yet in must code.
No, we don't have it yet.
No, not yet. That's
Okay.
I think we should do that.
But in the flag, it option was there, so I tried once. I didn't get anything. So
no, yeah, that's true. Sorry.
yeah, I was trying one time and I didn't get any result.
Yeah, that's right. Yeah, that's right. Sorry. Yes, we should hide that. That's not there. Yeah, no, sorry. That's on the roadmap.
But you had
all these operations, it seems that they probably could also benefit from a GPU.
Yeah,
That's right.
that would be helpful. So these can also be parallelized.
Yeah, I think that the large matrix operations, it's perfect
Right.
to fit on the GPU. That's the one. I think that the
might get you
final slide.
15 hours to something manageable.
Yes, I think Vishnu should consider come to visit Oak Ridge sometime and try to see if you guys can work together. And they have a lot of experts out there, and see if you can implement part of the calculation on. And in particular, you mentioned about 14 hours. How many nodes you run on 14 hours for that calculation?
So for this calculation to compare, I've ran it on a single core because I wanted to see how much time it takes. Yeah, I wanted to see how much time it takes on a single core.
Okay. On single core. Okay.
Yeah, I mean, if we use more K points for this case, more nodes for this case, of course, this will lower the time, but that doesn't really solve the core issue. And also, we need significantly more K points than this. So the number of K points scales very quickly. So even with large number of cores, if we do say 100 cross 100 cross 100 calculation, which is sort of what I intend to do, it will still take a lot of time. But then that is only if you want to do a 9-atom, if you want to capture all the near neighbors. If we choose to just take, 3 or 4, or even just pair clusters, then it doesn't take much time.
But you didn't really do any convergence tests on each of the components of your equation. So you don't, or you know which part is not converging there, or did you just do it on this final conductivity or resistivity result?
Yeah, I tried some convergence tests. So we started with, so we didn't know it would take this many K points. So we started with, so if you look at the 96, so we started doing steps. So I think steps of 5 cross 5 cross 5. So we did 80. So we went to 70, 80, then we did 85, 90, then did 96. And then I think I did another calculation at about 102 or something, and it didn't change that much. So at this point, then
what I meant is, so you just did the convergence test on the final resistivity. So you didn't look at each of the components of your equation that leads to this. So you don't know where it's coming from, right? Or did you do that really? Did you, for example, I think on the equation 28 or something like that. I mean, that's something where you,
so it's
some K-point integration.
Yeah, so there's only one term that has K-point integration, and that's this term. So I don't know exactly if you're like what the functional form of this is that causes, like how the function looks like, and if how that correlates with why it requires that many K-points. But
Z1 is and Z is what here in this equation?
So this first term here is the only the only Brillouin zone integration term. So this is the term that requires large number of K points.
So I mean, this Z here is the energy, or what is?
Yeah, Z is energy. Yeah, energy.
I mean Z. Yeah, Z. I'm always yeah. Sorry.
Part of Atlantic now.
Yeah. So I'm getting confused of languages in the isolation. I'm sorry for that. Yeah,
also,
so
yeah.
I would just give you a tip. Try to look at the energy points close to the, because I did something on linear response, and I had problems with some energy points close to the Fermi level. So some crazy things happened there, and you really needed crazy K points to get some convergence. And like with playing around with the energy contour, I was able to get some better results there, but it was a hard work.
But also another, I think, trying to mention is we don't have to integrate over the entire Brillouin zone. So even though we are using large number of K points, we only have to integrate over the irreducible Brillouin zone. So for this case, we have sort of implemented the rotation. So that significantly also reduces computational time. And so even though we have that many K points, it does not take that much time because of that. So cubic symmetry, we only have to integrate over 1/48 of the Brillouin zone.
And also for Z1 and Z2, it's kind of relative to the Fermi energy, but with a little shift, delta. So what's the little imaginary part? How much is the imaginary part?
5 × 10⁻⁴ Rydberg.
5 milliripper?
0.5 milliripper. Yeah, so I did some convergence tests with that as well. So at about anything smaller than 1 milliripper, it seems to converge. Doesn't make that much of a difference. Yeah.
Yeah, sometimes you need to write it up, submit a paper about all these numerical details. I think that will be very useful. this convergence
see.
test.
So this formulation only work for metal or also for semiconductor?
Yeah, I think it should work, but we are measuring at the Fermi energy, so
Yes.
we are calculating Green's function at the Fermi energy. So I guess if you don't have any density of states at the Fermi energy, you may not get any conductivity.
Yeah, I guess for semiconductor, it's going to be conductivity is 0.
Yeah.
Yes, that's what like that's the way it's that's one.
Yeah.
Okay, any other questions?
As far as I know, also these things might work for thermal conductivity too, right? These Green-Kubo formulations. Do you have plan to apply that also, or?
Yeah, so I think we plan to use the electrical conductivity here, and then try to calculate Seebeck coefficients, and sort of use this expression, use the conductivity, electrical conductivity we get here, and then from that try to extract thermal conductivity due to electrons.
Oh, okay.
Any other questions? I'll stop recording. That's an excellent talk. Thank you.